So all we've done in this class so far, we haven't really done much of anything. We've talked about the environment in which semiconductors need to be, the actual structure of the atoms that need to occur. And we had to spend a lot of time talking about how we will determine their orientation and how they get sliced through and all that. And once we've gotten the structure of semiconductor devices, now we have to talk about how the charge carriers are actually found and how they move. So this is not going to take very long. This particular part of quantum mechanics, there is a lot to it. I'm just going to talk just a little bit about light and electrons and kind of what we know about them. And a lot of this stuff you may or may not have heard before. But first, before we start quantum mechanics, I always like to start and let you know what physicists think of quantum mechanics. When I grew up, my father was a physicist. Everybody he knew was a physicist. Physicists were super smart because they are actually super smart. And these physicists were all really at the top of their game. And this is what they had to say about quantum mechanics. Niels Bohr, very famous Danish physicist, won the Nobel Prize and basically said, if it's not shocking, you don't understand it. And this is a lot of the theme that goes through. Roger Penrose was an English mathematical science, and he said it makes absolutely no sense. Richard Feynman, who is absolutely wrote a couple really, really good books about his life. He wrote one called Surely You're Joking, Mr. Feynman. It's a great book. It's all about him growing up and working on the atomic bomb and all that. But he very famously said, if you think you understand quantum mechanics, then you don't understand quantum mechanics, which is good because I don't think I understand it. So that means I guess that still means I don't. I kind of do. But, and then Erwin Schrödinger, who's actually completely attached to this idea of quantum mechanics, and we're going to next week study the equation that he came up with to kind of quantify all this, and he says, I don't like it, and I'm sorry I ever had anything to do with it. So going into that, we're going to talk a little bit about how we got to this point. We're really not going to talk about the details of quantum mechanics yet. We're just going to talk about kind of historically how we got to the point we did. So first of all, at the end of the 19th century, so this goes back a ways, light was considered to be just electromagnetic fields traveling in waves. And basically, it traveled in waves according to Maxwell's equation. That's actually a picture of James Clerk Maxwell happily observing his electromagnetic wave with all of his equations above his head, for which we don't use at all in this class, which is probably good. My father's great joy was to go out to lunch with me and write all those equations down on napkins and then explain them repeatedly. So that's how I grew up. So basically, light was a wave and matter was particles. That's basically what they thought. And basically, all of those equations above his head gave characteristics about light. Basically, the two at the top were basically just Gauss's laws for electric charges and for magnetism. The two at the bottoms are Faraday's law and Ampere's law. You don't really need to worry about that because you're not going to have to remember that for any period of time. But that was sort of the idea, that electromagnetic waves were how light traveled. And there was all kinds of evidence for that. They had done all kinds of experiments. First of all, Thomas Young, who was a scientist back in the day, way, way, way back. I mean, this is like 1800, so it's a long, long time ago. He did these double slit light experiments where he would take monochromatic light and they would go through these two slits, and the light would either destructively or constructively interfere. So it wouldn't just shine through the two slits. There would be a kind of a pattern. I actually have a laser in my office that can go through a slit and make a pattern, but I didn't bring it with me. I left it in my office, sorry. But anyway, that basically was was a very common experiment, and that's one of those things that in physics class in high school they always show you, and you're like, cool, and you don't have any idea why it does that, but that was a very famous experiment. He described this experiment in 1803, and by the 1820s, that was pretty much what everybody agreed with, that light is a wave. There was other evidence. If you took a light and shined it through a little pinhole, you get that same kind of constructive and destructive interference. If you have light going through some kind of liquid or structure or something that bends it, it breaks up into different colors. So all of that experimentally told people that light was a wave. So basically in 1887, so not too long after this, but maybe sort of towards the end of the 19th century, Heinrich Hertz, who, if you've ever given any unit of frequency in hertz, that was the guy. He was the guy who studied that kind of thing. And he did this experiment where he would have monochromatic light hit some kind of material, and a photoelectron would be emitted. And he noticed that when the light would hit the material, if he made the light more intense, it didn't change the kinetic energy of the released photons. So he noticed that basically if he changed the frequency of the light, he got more energetic photons, not more, just more energetic, well, photoelectrons. But he really didn't take the time to figure out why. He just was like, oh, okay, cool. And then he went on with his life and really didn't ever figure out why that was happening. But it was counterintuitive, because one would think if you had light and you shined it on something and electrons were released, if you made the light brighter, you would have more energetic electrons. And that's not really what happened. What happened was if the light frequency changed, you would have more energetic electrons. If you increase the intensity, you would get more electrons, but they're the same amount of energy. So that was kind of noted, questioned, and kind of not forgotten, but just set aside, because nobody knew why that was happening, and Heinrich Hertz had other things to think about, so he really never did actually figure out why that was going on. So a while later, in 1900, so now we're getting into the century in which I was born, but not at that end of the century, obviously, Max Planck, who you may have heard of, he said, well, I think, and he was actually able to kind of show this, but he said that perhaps radiation, like thermal radiation, is released in packets. It's not a continuous energy thing. It's when this stuff is released, it has a certain amount of energy, and it can only have this amount of energy. So he postulated basically that energy existed in quanta, basically called it quanta. And so when he did that, the idea was, well, maybe light, when it's emitted, is not just a continuous thing, but maybe it's actually something more particle-like, as well as being wave-like, which was an unusual idea. And this didn't get put together until just a little bit later. Einstein, who has to come in to every class pretty much that I teach somewhere or another, he actually sat down and explained why the photoelectric effect was working, why it happened. And he was about the age he was in this picture when that happened. He was sitting around thinking, which he did very well. He didn't do really well with studying, but he did really well with thinking. And he was thinking about energy in general. And he thought, well, if energy has to be conserved, maybe when a photon causes an electron to be released, maybe any extra energy is turned into kinetic energy. And he actually came up with a formula that actually kind of described that, where the kinetic energy was basically based on Planck's constant, which is h, times the frequency of the light, and then you just had to subtract off whatever energy was needed to release it from the metal. And everything extra would just go into kinetic energy. And he got the Nobel Prize in 1921 for explaining that. And he basically explained the photoelectric effect. And what it said was that as the frequency of light goes up, and do be aware just that this little thing, that is a nu. I have to talk today for a minute about nus and velocity, and they look very much alike, so I'm going to point out which one is which. But that is a nu. And frequency is sometimes in F, and it's sometimes in nu. And they're exactly the same thing. It's just a lot of times the nu is applied to optical energy. And they were looking at optical energy, so that's why they categorized it that way. But it's the same thing. It's just two different letters describing the same thing. So basically, the light above a certain frequency on a surface emits electrons. Electrons are immediately emitted. If you get the light brighter, you get more electrons, but not more energy. And it's a function of frequency, the kinetic energy of the electron, not intensity. And that was kind of a big deal. It was a big enough deal that he won the Nobel Prize, so that's a good thing. So where does that go with us? Well, the maximum kinetic energy of an electron is Ke equals m, and that's a VEE, V squared. Anybody who's ever taken physics, you've seen Ke equals 1/2 mv squared. That's just how we describe kinetic energy. What he did was he took that and related it to h nu, and then this is nu, if I can spell it, nu naught, which means the frequency at which the electron is released. That value right here, hv naught, or mu naught, nu naught, this is why this is the end of the day, because I can't remember even what I'm talking about. Anyway, the h nu naught is called the work function. Later in this class, like when we start talking about metal semiconductor junctions, we will use that work function, because every metal has a work function. It's just the amount of energy it takes to release an electron. So when we get to talking about metals and semiconductors together, we will come back to that. You're not going to see it for a while, but you will see it again. So basically, the maximum kinetic energy was decided, and then we're still pretty much, they haven't really related this to electron motion yet. We're still talking about light and how it works with electrons. But this changed in, a little later in the 20s. There was a guy, Louis de Broglie. He was actually a history guy. He actually got a degree in history, and then because he was actually also, I think from what I remember, related to some kind of royalty also. So he already had plenty of funds. He really needed to earn more money. But he got this degree in history, and then he got, wanted to do something else. So he switched to math and physics because, of course, they're like totally related and all that. And if you're good at history, you might as well be good at math and physics. But he did. He changed to math and physics, and he was sitting around thinking one day, and he thought, well, light, we used to think it was a wave, and now we've also shown that it can be a particle. So he thought maybe electrons, even though we think they're particles, can also be waves. And that was kind of a really big idea. he brought that up. He postulated, he actually came up with an equation that related momentum of light and wavelength of light, and he actually found a wavelength that's related to the particle. And that we're not going to need too much again until later. I'm going to mention it again later, but I don't think I have ever asked anybody to find the de Broglie wavelength. Maybe I have. I don't know. It's really easy. It's right there. But he made this idea that perhaps electrons move as waves, even though they're particles. And they started doing experiments. And they did a double slit experiment with a stream of electrons instead of light. And they find they have the exact same thing happens. If you have a stream of electrons going through two slits, you will get interference and constructive and destructive interference patterns. And it actually ends up looking like that. If you have a screen and you have electrons going at two slits, you just end up getting more and more, and they make that regular pattern. They don't do anything different than what light does, even though they seem to be totally different. So, the only thing you need to take away from all this, because when we come back next week, we're going to get into the nitty-gritty of how electron movement as a wave works, because that's where Schrodinger comes in and actually comes up with a way of determining how we can figure out the function of the wave, which we don't do a lot of in here, which is probably good, because in some places you actually have to solve the wave equations, but you haven't had enough math to be able to do that, so I'm not going to make you do that. But basically, there's a whole set of frequencies in which different light exists, and there is a relationship between electron movement and light. And that's really all you need to remember from today. You don't need to remember anything else except that electrons move just like light in a wave pattern. And you don't really know where it's going to wind up until it gets there. And when it gets there, then it's there. Electrons are weird. And they're going to be even weirder when we start talking about how we quantify them, how we find them, how we determine how many there are. Because it's really hard, if you don't know where an electron is, to determine how many of them you have. And that's kind of the whole point of what we'll talk about next week.